Respected dignitaries, participants from the various institutions, and my dear colleagues. A very warm good morning to one and all. I, S. Reshma, Assistant Professor, Department of EEE, delighted to welcome you all on behalf of Gates Institute of Technology for Day 3 of 5-day Faculty Development Program on Emerging Trends and Challenges in Renewable Energy System, organized by Department of EEE, Gates Institute of Technology, Gutti. Now I would like to request to the E. Ramakrishna sir to give a brief introduction about the Day 3 speaker of this program.
It's my pleasure to introduce today's speaker, Dr.K.Manjunath sir. Sir presently working as an assistant professor in IIT RM, Ahmedabad. Sir has completed his PhD from IIT Hyderabad. To his credit, Sir has published in more than 20 international and national journals. Sir has completed 4 research projects. Thank you, madam, for giving this opportunity.
Now I request today's speaker, Dr. Manjunath sir, to take over the session on Synchro Converter control of inverter-based source for flexible PQ regulation.
Thank you, madam. Thanks for giving this opportunity. So I will share my screen.
Yes, sir. Yes, sir.
So I hope screen is visible to everyone.
Yes, sir.
Okay.
Yes, sir, it is visible.
Yeah. So good morning, everyone. So the title of my talk is Synchronverter control of inverter-based source for flexible power regulation. Okay, so here we are going to discuss about control of inverter when inverter is subjected to constant DC source and control of inverter when inverter is driven by PV source. So this is the intention of this presentation. And the outline of my presentation is, so initially I will introduce brief discussion. I will introduce brief about in control of inverter, then the objective and motivation of this presentation, and traditional control, followed by synchronverter or virtual synchronous generator. Basically, synchronverter is a combination of 2 words, synchronous machine and inverter. We are going to control inverter by incorporating the control features of synchronous machine. Okay, followed by parameter design of control loops, then simplified control, then solar PV driven grid and synchronverter. Conclusions, we will talk about few results and then references. Okay, coming to introduction, nowadays energy demand is increasing, generation is struggling to maintain energy balance at par with the demand. So renewable energy sources are supporting the utility grid by injecting available power without compromising the grid standards. Okay, so the typical features of renewable energy sources are, there are basically small scale power generation. If you take a thermal power plant, generation will be in megawatt. But when we talk about renewables, the generation may be few kilowatts, of order few kilowatts. So comparison wise, it is small scale power generation. And applicability of renewable energy is more appropriate at distribution level. So 400 volt, 230 volt line to neutral. So plug and play of renewable energy sources is more compatible at distribution level rather than transmission level. If you take synchronous machine in a thermal plant, the voltage level of generation varies from 11 kV to 25 kV in the context of India. But unlike synchronous machine in a thermal plant, a renewable energy source may typically plug and play at 400 volt. So that is the applicability. So these are the two important features. Okay, coming to power electronic converter. Okay, so power electronic converter is basically an interfacing device between renewable energy and utility grid. So we are going to regulate or control the power electronic converter as per the requirements. Okay, so few categories of renewable energy sources will deal with DC form of power and energy. Like solar PV is DC form of power, fuel cells DC form of power. So few energy sources deal with AC form of power, that is wind energy system or diesel generator. Although diesel generator is not a part of renewable energy, but still it sometimes support the energy demand. So moving further, so we are calling a device called voltage source converter. We are referring it to inverter. Inverter can be realized as a voltage source converter. The reason is the input of inverter is DC form of voltage source. The output of inverter is AC form of voltage source. So it is basically a converter, okay, which predominantly converts DC to AC by considering voltage quantity. That's why we call it as voltage source converter. Okay, so voltage source converter abbreviation is VSC. This is followed throughout any literature. In our presentation also, we will use the same notation. VSC can be represented in two ways. One is switched model, and another one is averaged model. So people who are concerned about harmonics, so who are concerned about THD, all this, we for such kind of work, we usually follow switched model. But people who are interested in terms of power system like power generation at the terminals of VSC, we will consider VSC as average model. So when we consider VSC as average model, the switching aspects are ignored. The output of VSC is considered to be pure sinusoidal, and we are going to regulate the power by considering the output to be pure sinusoidal. Okay, so in our work, in this presentation, I am going to consider voltage source converter by considering averaged model. Okay. Now, when we talk about PV panel, so it is true that it is DC form of power. If you take a single panel, it may give 30 volt and few amperes of current. VSC input voltage should be minimum of 650 to get AC sinusoidal of 230 volt line to neutral. Under such circumstances, you need to arrange the PV panels in series and parallel combination such that DC side voltage is minimum of 650 volt. So this is the connectivity requirement. So if you see the third point, connectivity pattern of sources, configuration, number of stages will be determined based on specifications of VSC. Okay, sometimes bidirectional converter is required, so number of stages will be more. Sometimes we follow conventional configuration, there it is a single stage. Okay, so these are we need to do groundwork before commissioning the entire system. Okay, so the control of voltage source converter is gaining importance, okay, because of huge participation of renewable energy sources. New control techniques are being explored in the literature for finding easy ways to inject the renewable energy into the grid. Okay, so when we look at the control aspects of VSC, okay, basically a VSC is driven by DC source. Okay, now we will give gate pulses to the inverter. These gate pulses are obtained by comparing sine and triangle. This is a well-known technique. It is called sinusoidal pulse width modulation. Another technique is also there, that is space vector pulse width modulation. So the terminal voltage magnitude and angle at the AC side of VSC can be regulated by varying the magnitude and phase shift of sine wave in SPWM technique. Okay, so in sine triangle comparison, if you vary sine wave, obviously the terminal voltage, AC side terminal voltage of VSC can be varied. So this is simple, and so by varying this SPWM, sine wave in SPWM, we are going to regulate voltage magnitude and angle. So this is simple. Another way is we need to control the VSC in synchronous DQ quantities. Okay, so if you look at the modeling of synchronous machine, there will be direct axis, quadrature axis. Okay, so ABC to by performing parts transformation, ABC quantities are realized into DQ quantities, and the advantage here is DQ quantities are constant quantities. ABC quantities are sinusoidal quantities. Controlling a sinusoidal signal is little complex than controlling a constant quantity. Because of this reason, because of this nature of DQ signals, we are making use of this advantage and control the VSC. And the last point is realizing inverter as a synchronverter. As I mentioned before, synchronverter is a combination of two words, synchronous machine and inverter, and combinedly we are speaking it as synchronverter. In a synchronous machine, there are two main loops. One is excitation control loop, another one is frequency control loop. Okay, these two control loops are incorporated for controlling the inverter to fulfill the requirement. So that is what is carried out in synchronverter architecture. Okay, so the motivation of this work, okay, is in view of participation of grid-tied renewables, we need to explore a simplified control for regulating the terminal power. And while doing so, among the mentioned techniques, synchronverter technique is selected. Why it is selected? The reason is application simplicity, ease of control parameter design, and number of measurements are very limited. Because of this circumstances, this particular aspect is selected. Okay, so coming to objectives of the presentation. Okay, so in this presentation, I am going to revisit the control parameter design approach, more importantly for frequency control loop. And second thing is to explore a simplified control technique where the loop is only one loop. Instead of two loops, just considering one loop, we are going to see what is happening. So these are the objectives of this presentation. Okay, so in introduction itself, I am going to convey the pros and cons or whatever the observation that we made when we employ control technique using ABC quantities and DQ quantities. So number of quantities in ABC is 3, A phase, B phase, C phase. Okay, number of quantities in DQ is 2. And we need to remember, for a balanced system, only positive sequence will exist. Negative sequence will not exist. Okay, if the supply is 3-phase balanced or it is a balanced 3-phase system, there is no zero sequence component, only DQ will be there. So instead of 3 quantities, we are dealing with 2 quantities. So something is better. So regulation is simple. Okay, so ABC quantities are sinusoidal, DQ quantities are constant. When the quantities are constant, linear control is applicable. When the quantities are sinusoidal, so linear control technique has its own limitation. Okay, so because of this reason, control implementation in ABC is complex, control implementation in DQ is easy. Okay, so okay, so yeah, so this is spark transformation. So this is the transformation where we are converting ABC quantities into DQ quantities. So this is power invariant DQ transformation. The reason is there is no constant or no multiplication factor for P and Q. It can be directly scaled. That's why it is called power invariant DQ transformation. For this particular transformation, the power relation P and Q is VDID plus VQIQ, and reactive power is VQID minus VDIQ. Okay, so this is conventional control. Before going to synchronverter control, let us discuss about the traditional control, that is DQ based control. So you can see the schematic. The upper figure shows the schematic diagram of inverter connected to grid when the inverter is driven by constant DC source. See here, there is no PV, just a constant DC source is kept here. So the power injected into the grid is defined by references PREF and QREF. From these power references, current references are computed. So those are called control commands. So these control commands will regulate, this current control will ensure that the actual current will track the reference quantities. So if you see bottom left figure is current controller. So the DQ components of current controller, since D and Q are constant in steady state, simple PI controller is sufficient. The only thing is you need to compensate Q component in D and D component in Q. That separation is shown after with the summation block here. Okay, so finally we are getting D and Q. So modulation components of D and Q is obtained by dividing with VDC by 2. So this is current control will ensure that actual current will track the reference. Okay, so this current control is a linear controller based upon the linear differential equation that has shown on the right part, bottom right part. So this is linear differential equation. So based on this linear differential equation, we are employing linear control, that is PI control. So we can see the control is something which we need to pay more attention for fulfilling the requirement. Okay. So let us come back to our main control. Okay, so this is conventional or traditional control of grid tied inverter. Now coming to our proposed control, that is the control of our interest, virtual synchronous generator or synchronverter. Virtual synchronous generator means we are realizing inverter as a synchronous machine. That's why there is no physical synchronous machine. It is virtual synchronous generator. Okay, as I mentioned before, two control loops will be governing the synchronous machine. One is frequency control loop and excitation control loop. So the swing equation is frequency control loop. You can observe that omega is a state variable. By mismatch in torque, mechanical and electrical torque, this J d omega by dt is basically torque balance equation. And next equation is excitation control loop, where the state variable is field flex. So we are giving excitation to rotor of a synchronous machine. So the rotor flex is a state variable. Okay, the mismatch in reactive power and deviation of voltage is realized with respect to mismatch in reactive power, and the same is conveyed in the form of state variable, state equation for field flex. So this is the governing equation for excitation control loop. So the first equation is frequency control loop and the second one is excitation control loop. Only by taking or including these two governing equations, we are going to regulate the virtual synchronous machine. Sorry, every time I am moving to introduction slide. Okay. So these are the governing equations. Okay, so if you look at the control architecture, the foundation of virtual synchronous machine is introduced by this Professor QC Jong. Okay, and the title of this work is Synchronverters, inverter that mimics synchronous generator. It was introduced in 2011. Modified versions are now reported till date in the literature. So the two equations that I shown in the previous slide is here. You can see this is the upside, the governing equation of frequency control loop is mismatch in electrical and mechanical torque. So mechanical torque is obtained from power set point, active power set point, and electrical torque is computed from equations. Okay, the mismatch is processed to 1 by JS block, and this block will give frequency. Upon integrating the frequency, we will get the phase shift. So this is frequency control loop. The down part is excitation control loop. You can see that mismatch in QREF and Q along with voltage deviation component is processed through 1 by Ks, and one output of 1 by Ks is field flex. So field flux is represented as product of mutual inductance and field current, M of IF. Using these quantities, we are going to generate the voltage command, and that voltage command, that is sinusoidal form of voltage, is given to PWM block, and PWM block will generate the gate pulses for the inverter. See, only two loops. So the two loops are represented in control block diagram here. Okay, so in the block diagram, you can see equation 1, 2, 3. So the equation 1, 2, 3 is basically, sorry, here the number is wrong. The torque is computed from field flux and currents. Voltage is computed from omega, field flux, and sinusoidal form of phase shift. Active power is computed from field flux, omega, and current components. Reactive power is computed from field flux, omega, and cosine of current components. Using this, we are going to control the inverter. But this is all thing is represented in ABC quantities. There is no particular thumb rule that we have to incorporate synchronverter control by using ABC quantities only. We can also do it in DQ quantities that we will discuss further. So there is some application flexibility associated with synchronverter. Okay, the torque and power components, active power, torque, whatever the shown in the previous slide, that can be computed in either of ABC domain or DQ domain. Okay, so in the previous slide we have shown by using ABC quantities, and the same is computed using DQ quantities also. So this is the first application flexibility. You can define or you can obtain the control architecture in any of the domain. Okay, so in the literature, in the foundation work, okay, all the quantities are considered by considering field flux. You may or may not consider. Without consideration of field flux also, you can compute torque and power. Okay, so that we will so this is another simplified version. Here I am going to use only one loop, frequency control loop. The reason is, in the context of India, people will get benefit when they inject active power. Okay, in many of the regions, injecting reactive power is considered as an ancillary service. You may or may not be paid. Very recently, reactive power pricing is coming into picturization. But overall, if we see, reactive power support is treated as an ancillary service. So here we will focus more in active power injection. So here we are instead of going for excitation control loop, whatever the grid voltage is there, that is defined grid voltage for obtaining the sinusoidal signal for PWM circuit. The only thing is frequency control loop need to be incorporated here. Okay, so whatever the current injected into the grid multiplied by grid voltage will give you power. Upon dividing power with omega, that is angular frequency, you will get torque component. So reference torque component from reference power, actual torque component from actual power, and the mismatch is given to 1 by JS block, that will give frequency. Okay, so if you do integration of omega minus omega g, that will give you phase shift. Using grid voltage and phase shift, it is sufficient to generate a sine signal for computing sinusoidal pulse width modulation. Okay, so here this work is considering only frequency control loop. We are not going to consider voltage control loop because injecting reactive power may not be benefit for end user. Okay, so here if you look at it, so the power injected into the grid is basically product of voltages upon reactance multiplied by sine component of phase shift. Okay, this is well known. So the delta in the above equation is computed as per the previous block diagram, integration of omega minus omega g dt. So this way we are going to compute delta. Okay, so as I mentioned in previous just before, power can be computed in any of the domain. If you go for ABC quantities, we have to compute the instantaneous power using VTIT, VIA plus VBIB plus VCIC. If you use in DQ components, VDID plus VQIQ. So power computation can be performed in either of the domain, ABC or DQ. Okay, so if it is ABC, okay, if it is ABC, you have already computed delta by integration of omega minus omega g, and you know the grid voltage peak value Vm. With these two, you can generate three sinusoidal quantities. So this is when we go ahead with ABC based computation, that is bottom set of equations. When we go for DQ based computation, what is phase shift delta? Delta phase shift is the phase shift between two voltage phasors. What are those two voltage phasors? One is terminal voltage of VSC, another one is grid voltage. So this phase shift is delta. Okay, so we have to realize the horizontal and vertical component of delta. Horizontal component being cos delta and vertical component being sin delta. Okay, using this, we are going from grid voltage and reference phase information, we are going to compute the terminal voltage of VT. If you see bottom set of equations, peak value of grid voltage and phase shift, we are going to compute ABC quantities, or else you know the grid DQ quantities and delta information, we are going to compute the terminal voltage. So the top representation is for DQ and the bottom representation is for ABC quantities. This is how we generate sine wave. Okay, now coming to parameter design, okay, which is very important. So if you look at the control representation in frequency control loop, there are two control parameters. One is J, another one is D. J being moment of inertia and D is droop related to torque and omega. Okay, so here droop is computed using mismatch in torque upon mismatch in frequency. Okay, so mismatch in torque and mismatch in frequency, we know very well that we are maintaining very compact band. So frequency mismatch is very less margin. So delta omega should be as minimum as possible, and parameter J can be obtained using any linear analysis. So here the closed loop representation of active power. Okay, so P is reference power. Upon dividing with omega nominal frequency, we will get reference torque. Okay, now this is the closed loop diagram of frequency control loop. Upon integrating omega, we will get theta. Okay, we know very well that product of Vg Vt upon x sin theta is active power. For smaller values, sin theta is approximated to theta. So here on the right hand side, we will get P. So when we compare with reference P, we will get the delta P mismatch. So you can use any linear analysis, linear control systems for getting J and D. Okay, so basically overall in that literature also, they will assume some time constant for this loop, and by fixing the time constant, they will go for J and D, assignment of J and D control parameters. Okay, so here I am going to discuss a small case study with results. So let us see. The inverter is 10 kVA inverter. Okay, it is connected to a 400 volt line to line 50 hertz grid as per Indian standards. Okay, the interfacing inductance is 2 millihenry. Okay, the inverter rating is P is 10 kilowatt. Okay, now this is one equilibrium when it is pertaining to 10 kilowatt. When the power injection is 10 kilowatt, the values of remaining quantities that we are using in this loop is this much. So for this equilibrium, we are going to do a case study by considering 4 different cases. Okay, first, if we assign D, what will be the value of J? Or if we assign J, what will be the value of D? So 4 cases are there. Okay, so D is droop gain. Okay, first we will assign droop gain by considering minimum frequency deviation. Okay, by considering minimum frequency deviation means frequency of 0.5 hertz on either side of nominal value. If we do the computation, D is coming around to be this value 10.13 Newton meter second per radian. With this, using linear control, if I do tune J, J is assigned with this value. Okay, and the vice versa is done in remaining cases. Matlab, G is tuned first, followed by D. So this is the procedure of tuning for 4 different study cases. So if we do it once we assign J, so J is, you can take practical specifications of 10 kVA synchronous machine. Okay, 10 kVA synchronous machine, what will be the mass, rotor mass, moment of inertia. By that practical circumstances also we can assign J and then tune D. Okay, we will do a comparative study. Okay, now in this case study, so system operation is initiated at t equal to 0 seconds. At when the time instant is 6 seconds, reference power is switched from 10 kilowatt to 5 kilowatt. So earlier it is 10 kilowatt, now it is switched to 5 kilowatt. See, in all the 4 cases, we are attaining new equilibrium, 10 switching from 10 kilowatt to 5 kilowatt. But the transients are different. You can see case 1 is having more transients compared to remaining cases, and which case is outperforming. The smooth transition is happening with regard to case 2. So that is this one. The parameters are 1 kg meter square and 32.81 Newton meter second per radian is giving a smooth transition. So this is the first case study in our presentation. For the same parameters, the frequency dynamics you can observe in this plot. Here also case 2 is outperforming others, and as usual case 1 is having more transients. And more, one good thing is all the 4 cases we are attaining new equilibrium. Okay, and this is delta. Okay, when we inject 10 kilowatt, delta is 0.04, but when we switch it to 5 kilowatt, delta is something close to 0.02. Okay, the variation of delta and P follows the same dynamic pattern, so that you can observe here. So this is P dynamics and this is delta dynamics. So they will be follow the same pattern of dynamics. So here also case 2 is outperforming the remaining cases. Okay. Now, in this case study, in the previous case study, our important loop is frequency control loop, and we are avoiding voltage control loop by defining grid voltage. But let us question ourselves, what is the complexity associated with voltage control loop? If we consider voltage control loop, the governing parameters are 2. One is K and then another one is droop gain associated with Q loop. So by definition, the droop gain dq is mismatch in reactive power upon mismatch in voltage. Okay, so here also the value of k is assigned by considering a time constant. There will be some execution time with the loop. That time constant of execution of loop is considered for defining the parameters. Okay, so this is actually followed in literature. Okay, so what is complex in here? When we see active power loop, it is linear. Let us come back to active power loop. You can see the top loop, it is linear. So easy to design J and D. Okay, when it is bottom loop, sorry, when it is bottom loop, so here there is some non-linearity. You can see the reactive power expression is non-linear. So this is reactive power expression. So if you look at the expression, it is non-linear. When it is non-linear, linearization, we have to go for linearization and go for parameter tuning. Or else you can apply non-linear control for regulating the quantities. Okay, which is not straightforward. Because of these difficulties, reactive power regulation of inverter is little bit challenging, I can say. It can be done, but there is some complexities associated with it. Either we need to proceed with rational assumptions or else go for some kind of nonlinear technique. So that is what is happening with reactive power loop. Okay, so to overcome these problems, With only one loop, we want to regulate both P and Q. How this can be done? This can be done by considering some calculation component in the control loop. So that we are going to do in a simplified approach. That is the second part of our presentation. So let us look into it. If you have any queries, you can interrupt in the middle of the presentation because I am moving without any interaction. So I am happy to interact with you. Uh, you can stop me at any point of time and ask for any queries. Okay, so these are the general governing equations for active power and reactive power. Okay, so generally grid voltage is reference. So when grid voltage is reference in phasor form, it is Vg at an angle of 0. The terminal voltage of inverter is having some phase shift. So in phasor form, it is Vt at an angle of delta. So with these phasor voltages and complex impedance, the governing equations for active and reactive power is this one. Okay, so there are two equations. You can compute two unknowns. The two unknowns are Vt and the two unknowns can be anything in this governing equation essentially. So two equations, two unknowns, there will be a unique solution. Okay. Now the red color control loop is the simplified loop. So the first control loop is the straightforward control loop, and this is which is modified. So the modification part is shown in red color, and the remaining thing is as discussed before. But what is new here? We are going to compute the phase shift by integrating omega minus omega g. When this phase shift delta is obtained from VREF is computed as per previous mathematical relationships with regard to P and Q. When VREF is known, we can get horizontal and vertical component. Horizontal component is D component, vertical component is Q component. So these DQ components, by using inverse transformation, we can get the ABC signals. Those ABC signals are carry forward for SPWM circuit and generate gate pulses to the inverter. So what is doing here? We are computing VREF from both P and Q. We are computing VREF from both P and Q, and we are avoiding the QV regulation. Reactive excitation control loop we are avoiding by incorporating this VREF. So why we are avoiding? As I discussed, it is defining the control loop or assigning the parameters is not straightforward. So, so this is the horizontal component you can see here, and this is the vertical component. So this is very much evident from phasor diagram. The phase shift between grid voltage and terminal voltage is delta. So delta, the horizontal component of delta is Vt cos delta, and vertical component is Vt sin delta. Okay, for the transformation shown in the beginning, there is a multiplication factor, root 3 times of RMS value. Okay, so this is the second case study of our presentation, where we are going to observe whether the actual quantities are tracking the reference quantities or not. So in this case study, again, we have considered 4 cases. The 4 cases are pertaining to 4 different R by X ratios. So you can see the R by X ratio is 0.01, 0.159, 0.9 and 2.5. So from a range, if you look at the range is from 0.016 to 2.5. Why this range is taken? This is as per IEEE standard distribution feeders, 9 node distribution feeder, 13 node IEEE distribution feeder. From these feeders, I have seen the data. The ratio varies from 0.9 to 2.5. So to have some coherency, in the same ratio, we varied the R by X. From the first case study, case 2 is outperforming in the first case study. So the control parameters of case 2 are slightly taken for this case study. Okay. Now this is the reference for VREF and torque reference for different switching cases. First switching is from 10 kilowatt to 5 kilowatt, reactive power switching from 2 to 4. So essentially, we are reducing active power and increasing reactive power in the event of switching. So let us see what is happening. So active power is reduced from 10 kilowatt to 5 kilowatt. So the same thing is happening in the simulation? No. Sorry, it is happening. 10 kilowatt to 5 kilowatt it is happening. But again, look at the transients. The transients are not same in all the four cases. Okay. So you can see there is some sluggish response in case 4. So this is about transition in P. What about transition in Q? We have increased from 2000 to 4000. Are we achieving the same? Yes, of course, we are achieving the same in all the four cases, but case 4 is sluggish. Sluggish means slow response. So the slow response is always deteriorate the performance of the system. We always want a smooth transition. So smooth transition is something like case 2 is again having the smooth transition if you observe the dynamics. Okay, so this is switching of P and Q and variation of terminal voltage. When you switch Q, obviously there will be a switching in voltage. So that is happening here. Since the R by X ratio is very high in case 4, the voltage magnitude will also be very high. The reason is more impedance will give more voltage drop. When there is more voltage drop, there will be high value of Vref. Okay, so this is delta dynamics. This is delta dynamics. Okay, so again here you can see case 4 is slow response. So steady state is attained after good time period. But whereas case 1 and case 2 they are ensuring smooth transition. Okay, so as of now we have seen two case studies. First case study is with regard to control parameter. Second case study is with regard to different R by X ratios. Second case study we are going to regulate reactive power with only one loop, single loop. Now coming to the third part. So what is difference between first two case studies and this? The difference is inverter is driven by a constant DC source in previous two case studies, but here in the place of constant DC source we are going to consider this PV panel. When it is PV series and parallel combination of PV panel, okay, PV is a current source basically. If you look at, sorry, I will present now. Again. Coming back to our discussion with a small interruption. So in the third case study, inverter is driven by a DC source in previous two cases. Here inverter is driven by a PV panel. PV panel essentially is a current source. When you arrange PV panels in series and parallel combination, the effective terminal voltage should be controlled. In order to control the effective terminal voltage, definitely you need to place a DC link capacitor. When you place a DC link capacitor, the capacitor current is a state variable, that is C dV by dt. When it is appearing as a state variable, the variable is VDC, this equation you see. When it appears as a state variable, you can control that particular component, that particular quantity. Okay, so that's why a DC link is definitely required when you arrange PV panel in series and parallel combination. Okay, the control architecture will remain one and the same in accordance to our previous discussions, but here because of this placement of this capacitance, you need to modify a little bit. What is that little bit? Let us look into here. So this is DC side of the system. So here you can see PV voltage, PV current. Okay, and here it is ID current. If you apply energy balance equation is incoming power minus outgoing power is basically energy associated with capacitor. Sorry, rate of change of energy associated with a capacitor. Rate of change of energy is active power. So this is called power balance equation. Incoming power minus outgoing power is basically power associated with the capacitance. Okay. Now, when you see it, it is a differential equation where you can observe that first order differential equation where VDC square is the state variable. Okay, employing VDC square as a state variable will impose some computational burden on the controller. To overcome this problem, we follow the downside equation. Okay, instead of power, we can represent the current balance equation. Power balance equation is replaced with current balance equation to get the state variable in VDC form. That means incoming current IPV minus DC current is basically capacitor current. Okay. Now, this is the control architecture for this equations. The applied control architecture is this one. Okay. So, PV power, voltage and current of PV power is taken to get regulated power point algorithm. It need not be a maximum power point. It can be any equilibrium. It can be MPPT also, other than MPPT also. That's why I have mentioned here regulated power point algorithm. So this algorithm will give you the DC reference DC component. So the reference DC component is compared with actual DC component, and the error is processed to linear control. Error is delta VDC. So this delta VDC can be given to linear controller based on the differential equation shown before. Okay, so the error will get either power or current. If you follow power balance equation, the output of controller is power quantity. If you follow current balance equation, the output of controller is current. So essentially here it can be IPV also, either PPV or IPV, either PPV or IPV, and here it is IREF. Okay, so with this understanding, we will do a small case study. Okay, so these are the specifications of this case study. So a panel configuration is selected pertaining to sun power, and the module name is this one. So how many series and parallel strings we have? We have taken 11 series strings and one parallel string. Okay, for the case study, we need to define the temperature and irradiation level. So the irradiation considered to be this much, and the temperature is considered to be this much. Okay. Now, for this scenarios, for this particular temperature and irradiation, the possible PV power is this much. Sorry, 700 watt. Okay, as usual, VSC rating is 10 kVA. DC link voltage minimum 650 is required to maintain compatibility standards with Indian grid. So 650, in the place of 650, we are maintained a little higher, 735. And KPKI values of the previous control diagram is found to be minus 35, minus 100. Okay, that is tuned using classical control. And the value of DC link capacitance is 0.01 farad. Interfacing inductance is 1.35. This inductance have some internal resistance, that is 0.3 ohm. You can see the control parameters are selected based upon the performance of previous case studies. So they are found to be these values. So with these values, let us see what is happening with simulation. Okay, so these are IV. IV means current voltage characteristics, power voltage characteristics of the selected PV configuration. Okay, and these are the simulation results. See, this is PV voltage. Okay, the red color value is power pertaining to PV. So it is close to 700 watt. Okay, but the actual power delivered by the inverter is having some transient in the beginning, but after some time our actual power and PV power is tracking. See, after 5 seconds it is almost the same. The reason of this transient is because of the control values, or else appropriate design of control parameters of frequency control loop, or else DC link voltage control loop. Okay, you can see the initial high transient is due to initial high voltage of this DC link. DC link voltage should be maintained at 735, but initially it is close to 800. This might be the reason, and the and the frequency as per frequency control loop is also higher. Because of these two reasons, the transient is huge in the beginning, but these two transients are also allowing power to drop from the grid in the shaded region, which is not a safe option. Since it is 700 watt, you are getting a transient of 1300 watt, means almost twice of the defined, which is, let us say, if you are injecting 10 kilowatt, you are not supposed to give 20 kilowatt surge. So which is indeed a problematic. So this problematic is due to not having better choice of control gains. Okay, so therefore the analysis are always important. Studies, analysis, any mathematical work has its own advantage, because of having groundwork will facilitate you to commission for the actual system. Okay, so this is results with regard to thought, and the conclusions of my presentations are, okay, so in the first work we have injected only active power by defining reference as grid voltage. Okay, voltage control loop is not considered because we are not interested in injecting Q. In the second work, we have taken single loop only for injecting both P and Q for different R by X ratio. That is also fulfilling. And the third work, with the participation of PV and DC link capacitor, how the control structure is modified. So the control structure is modified by placing DC link voltage controller from power balance or current balance equation. So this is outline of my conclusions for today's presentation, and these are the references. The foundation work is done by Professor QC Jang, that I have placed as very much first reference, because all the basis of this work is for this reference only. And apart from that, the new developments are also included here. The new developments are somewhere reported in 2021 IEEE journal, and see, you can see here May 2020. This is also very good journal of modern power systems and clean energy, and recent report is IEEE transactions. So these are all modified versions of foundation work. All recent developments by due consideration of the foundation work reported in 2011. So that's all from my end. I would like to interact from the participants. I would like to listen from the participants. So any participants can come forward, and we will have some kind of discussion with regard to this work. I will be happy in interacting with the participants online or offline present who are available there. So excuse me, madam, or who else available?
So thank you, sir. Any queries from the audience? So if you have any queries, please post in the comment box so that sir can answer regarding your doubts. So any queries, please, from audience side, you can ask, you can text in the comment box. So if you don't have any queries, we can close the session.
Okay, sir, thanks again for giving this opportunity to share my work. Uh, so if there are no queries, then I can close the session.
Okay, thank you, sir. Thanks for your presentation, valuable presentation, sir. It's time to make a vote of thanks. So on behalf of EEE department, today I took this opportunity to put all my gratitude in the form of words. First of all, I would like to thank our today's eminent speaker, Dr.K.Manjunath sir, for accepting our request and for giving such a wonderful presentation on Synchro Converter controller of inverter based source for flexible PQ regulation and making even meaningful and interesting. Thank you very much, sir. And I would like to express our profound gratitude to our correspondent, Srimati V.K. Padmathamma Madam, Managing Director, Raghunath Reddy sir, and Director, Sri Vani Madam, and Principal, Dr. Syed Suraya Madam, for their constant support and encouragement. Thank you, one and all. Finally, at the end of the session, I would like to thank all the participants for this FDP from various institutions for their glorious presence. Thank you, everyone. Thank you all. Once again, thank you, Manjunath sir. Thank you.
Thank you, sir.
Thank you, sir. Thank you so much. So I'm closing the session.
Proceed.